Okay. Thank you, Professor Song. First, I would like to thank Professor Song for this kind introduction and the invitation, and also thank you for organizing this ARL seminar series. I personally learned a lot from it. So today I'm going to introduce our recent work on achieving sample efficiency in reinforcement learning with large state spaces. And this is joint work with my wonderful collaborators, Shijin Zhaoran, who is also here, and Professor Mandy Wang, and Professor Michael Jordan. And this work appears in NeurIPS last year, and the full version is also available on arXiv. So this work is motivated by the recent success of deep reinforcement learning. And we all know that deep reinforcement learning has achieved tremendous empirical success in solving complicated sequential decision-making problems. And usually these problems has high-dimensional inputs. And to handle those high-dimensional inputs, we utilize deep neural networks, which learns a good representation of those high-dimensional inputs, and build on top of those inputs, those representations. We use reinforcement learning to handle the decision-making part. And with sufficient amount of training data and computational resources, deep reinforcement learning has achieved tremendous empirical success, and their performance can be as good as human or even better than the best human being. And those successes spans many areas, including playing games, robotic control, interaction with human, and system design. However, deep reinforcement learning is not a panacea for all sequential decision-making problems. One of the most salient challenges of deep RL is that these methods are really data hungry. In other words, the number of data required for the success to happen is an astronomical number. And in many applications, we only have limited data, or it can be very costly to acquire new data, or the data generating process can be slow. And in those scenarios, because we have insufficient data, but we need massive data to achieve the success of reinforcement learning, and with only finite data or insufficient data, and we use those data to learn a model or fit some function in deep RL, the statistical error may be large, and such a large statistical error might lead to unreliability. And in addition, another drawback caused by the sample inefficiency is in the computational side. So massive data means we need massive computation, and also a longer training time. So if we don't have enough computational resources, then we might just don't have enough time for waiting the convergence to happen, and we will terminate the training process before convergence. And such a lack of convergence is another source of unreliability. And I would like to highlight that these two kinds of unreliability, the first one is about statistical side, and the second one is about computational side. They are both caused by the sample inefficiency of reinforcement learning. And with that in mind, if we want to deploy deep RL to problems in critical domains such as personalized finance and personalized healthcare and autonomous driving, once the deep reinforcement learning algorithm is unreliable, the potential cost will be huge. So the goal of this work is to develop a sample efficient reinforcement learning algorithm. And moreover, we would like this algorithm to be also computationally efficient, and also it will be able to handle high-dimensional inputs by using functional approximators. And in particular, we focus on the online setting where the agent interacts with the environment and repeatedly, and it learns how to get the optimal decision-making rule, which is called policy, by iteratively interacting with the environment and learn from its past experiences. And for such a setting, for such an online setting, one of the fundamental challenge is this exploitation trade-off. Here, and in reinforcement learning, this particular exploration is known as deep exploration, because reinforcement learning deal with sequential decision-making problems. So whenever we make a decision, we need to consider its long-term effect, and this is called deep exploration. And another source of challenge comes from high-dimensional inputs. Because we want to deal with high-dimensional inputs, the number of data, the number of all possible states can be infinity, and we need to use functional approximators to extrapolate information among states. So in particular, to achieve sample efficiency in this online setting with large state spaces, there are two coupled challenges. The first challenge is in terms of function estimation, because we use function approximator in this DRL, in this reinforcement learning algorithm. As a sub-problem, we need to fit some function using the data. But here, our setting is an online setting, so our data is adaptively acquired. So that means the first challenge we need to tackle is we need to be able to assess the estimation uncertainty based on the adaptively acquired data. And another kind of challenge we need to address is exploration. And here, because we use function estimators, we need to construct exploration incentives that are tailored to function approximators. That means in this setup with large state spaces, the exploration problem is more challenging than that in the finite reinforcement learning problem, because when the state space is finite, then we can just exploration problem is relatively easy. Well, we can just try to enumerate all possible combinations of state action pairs. But for our case, this is infeasible, because the state space can be infinity, and most of the states are not visited. So we need to, in terms of exploration, we also need to utilize function approximation tools to extrapolate information among states. So that means we need to construct some exploration incentives that is specific to function approximators we use. And now I would like to just give an overview of our result. And the details will come later. So in this work, we propose a online reinforcement algorithm which achieves both sample efficiency and computational efficiency. And also we incorporate functional approximators, including RKHS and over-parameterized neural networks. And in terms of algorithm design, our algorithm is based on a classical algorithm called least squares value iteration, which solves the reinforcement learning problem by fitting a sequence of least square regression models. And for this is a classical algorithm, and our algorithm adds an additional ingredients to it. We propose to, instead of using the least square point estimators, we propose to additionally quantify its uncertainty and this uncertainty of the point estimator actually reflects the uncertainty we have about each particular state action pair, and this gives us the information about exploration. So with that in mind, we propose to add the uncertainty to the least square point estimator and obtain an upper confidence bound. And then we update our algorithm using this upper confidence bound function. And by doing this, we directly make a trade-off between exploration and exploitation. And in terms of theoretical guarantees, our algorithm achieves a sublinear regret. That is, regret grows with a number of repeated experiments in terms of square root, in terms of its square root. And here, T is the number of repeated experiments the agent has. And H is called horizon, which is the number of decisions the agent make in each reinforcement learning problem. And this delta F quantifies the complexity of the function class we use, and its detail will be given in a later slide. And so this sublinear regret means that our algorithm means on average, the average error of this algorithm decays to 0 at a sublinear rate when T goes to infinity. So that means our algorithm is sample efficient. And moreover, both the least square value iteration point estimator and the uncertainty quantifier can be computed in closed form, at least for RKHS setting. And it can be efficiently computed when over-parameterized neural networks are used. And in other words, our algorithm also achieves computational efficiency. And for deriving these theoretical guarantees, we do not impose any sampling assumption. Our data is obtained by directly interacting with the environment. And the only assumption we make is a structural assumption which says that our function class has no approximation bias. And now I would like to directly jump to the details of reinforcement learning. I will briefly introduce some background of reinforcement learning. I believe the audience are very familiar with this. So our model is, we consider this episodic MDP, Markov decision process model. So in MDP, agent interacts with the environment in the following paradigm. At each time step, it observes the current state and takes an action and observes the immediate reward given by the reward function, and also the state evolves to a next state according to the Markov transition kernel. And here, both the reward function and the Markov transition kernel are unknown to us. And this, in particular, we focus on the episodic case, which means that the number of interactions between the agent and the environment is a finite number, which is given by this capital H. So starting from the initial, and also a policy is a mapping from the state space to the action space, which specifies how the agent takes an action at each time step. So starting from the initial step, the agent observes the current state and outputs an action according to the policy, and then it observes the first reward, and the system evolves to the next state S2, and then the agent takes the second action according to the policy and gets the second reward, etc., until the capital H time step is reached. And so the observation of the agent is just the trajectory obtained by executing this policy, which consists of capital H tuples, and each tuple consists of the current state, current action, and the immediate reward. And after executing the policy, the agent collects all the rewards, and the sum of these rewards, the expected value of the sum of these rewards quantifies the performance of the policy, which is also known as the expected total reward. And our goal is to learn the optimal policy which maximizes the expected total reward. And so when the model, so how do we get this optimal policy, which is quantified by the celebrated Bellman's equation? So in particular, we know that the optimal policy is known to be the greedy policy with respect to the optimal value function. And this optimal value function Q star actually is a set of h different functions associated with each time step. And what's the meaning of this Q star function? For each h, and for each h, the QH star evaluated at each particular S and A is equal to the sum of the reward, assuming that at the h time step we are at state S and we execute the action A, and afterwards we execute the optimal policy. And this function can be computed using the dynamic programming principle. And this is also known as the Bellman's equation, which says that the QH is equal to the sum of the immediate reward plus the one-step look ahead. And this one-step look ahead can be computed using the optimal value function associated with the next step, h plus 1. And we can write the right-hand side of this Bellman's equation in terms of the Bellman operator. And because we consider this episodic case, there's no reward after capital H time step. So in other words, the very last value function, QH plus 1, is a 0 function. So starting from here, we can go backwardly and use dynamic programming to compute all those optimal value functions. And I would like to remark that for evaluating this Bellman's equation, we need the knowledge of the reward function and the Markov transition kernel, but these two are both unknown to us. And so we need to use a data-driven method to approximately compute the Bellman's equation and get the optimal value function. And because the number of state can be infinity, we need to incorporate some function approximation, some function approximators to estimate the Bellman's equation. And by function approximation, I mean we need to utilize some parametric function class to approximate this Q function or the right-hand side of the Bellman's equation. And some of the examples include the linear functions and neural networks. And so now I would like to introduce our algorithm. So we recall that we consider this online setting. So the interaction protocol is as follows. The online agent interacts with the environment and by executing the policy. So it first initializes the policy pi1 and then execute it, get a trajectory, and then the agent will add this new trajectory to the data set. The data set is initialized by an empty set. And then with the current data set, it uses a reinforcement algorithm to compute an updated policy. And this step is a component we need to design actually. And this updating rule takes the current data and the function class as the input and give us an updated policy. And once we have the updated policy, we'll execute this updated policy again and get a new data and repeat this loop. And this loop continues for capital T episodes. And to measure the sample efficiency, we use the notion of regret, which is defined as the difference between the total amount of reward obtained by the Oracle optimal policy and the sum of the rewards generated by the online agent. And in terms of how to get this updated policy, a classical algorithm is called least squares value iteration, which just takes a current data set and the function class as the input and get the output, get an updated policy by fitting H regression problems. It's a data-driven analog of the Bellman's equation. Recall that the very last value function is a zero function. So starting from here, we solve a regression problem to estimate the right-hand side of the Bellman's equation. And where in this regression problem, both the response and the covariate are obtained from the current data set. And the regressor is given by the function class we use. And the regression target is the right-hand side of the Bellman's equation. After having the point estimator, we will just get an updated policy using the greedy policy with respect to the point estimator.
I was really excited to.
So is there a question?
No, I don't think so. Please keep going.
Oh, okay. So for the success of this method, we need to, for the success of LSVI, what we need is that the regression error of at each step is small. And to ensure this, we need two kinds of conditions. The first condition is that the function class captures the target function, which is the right-hand side of the Bellman's equation. So that means the function class has no approximation bias, or we need to somehow, or we can somehow balance the trade-off between bias and variance. And the second condition is that the data set is regular. So ideally, it should cover all the state action space, or at least the trajectory induced by the optimal policy, because the optimal policy is the thing we want to eventually get. And by saying that the policy covers the optimal trajectory, what I mean is that the empirical distribution of the data should be very close to the distribution of the trajectory generated by the optimal policy. But because we are in this online world, the data set is actually collected on our own, and so we need to design an efficient exploration mechanism such that we can gradually drive the data set to make it as close to the optimal trajectory as possible. So this is also known as exploration-exploitation trade-off, and which is fundamental in all kinds of online decision-making problems. And in specific to reinforcement learning, this exploration problem is more challenging than say bandit problem, because we are dealing with a sequential decision-making problem. And when H is large, that is the horizon is large, the difference is more evident. So which is given by this toy example. So suppose we start from a common initial state, a fixed initial state, and after that there are two kinds of state. The first kind is a good state, and the second kind is a bad state. Suppose at each good state, there are only the first action B1 will keep us at a good state, and other actions will all lead us to a bad state. And if we are at a bad state, no matter which action we take, we will remain at a bad state. And at each good state, in those intermediate good state, the reward is all zero, and eventually we will achieve a very huge amount of return given by this treasure chest. And in all bad state, we have a very small piece of return. And suppose we execute a random policy for exploration, then the probability of achieving the treasure chest is this probability is exponentially small, where H, the horizon, shows up in the exponent, and so which is inefficient. So in terms of achieving sample efficiency, we would like to have a regret bound which scales sublinearly in T and also polynomial in H. So this is what I mean by deeper exploration. And I would also like to note to remark that suppose we have generative model which takes any state action pair as the input and outputs an immediate reward as the next state. Suppose we have a generative model, then for this challenging exploration task, it can be very easy to solve. We just enumerate all possible state and action and see what the immediate reward and the next state is. Then we can easily identify that this path is the optimal trajectory. And in terms of prior existing literature on achieving sample efficiency in this online bandit and reinforced learning literature, for the when the number of states is finite, when the horizon is equal to 1, there are classical results about multi-arm bandit and contextual bandits. Here, contextual bandits means allows the number of states to be infinity, and these works incorporate linear or kernel function approximators to represent the reward function. And these algorithms, because they use myopic exploration mechanisms, they cannot be applied to reinforced learning. And also, there are classical works focused on finite MDPs and get sample efficiency. And in terms of reinforced learning with functional approximation, there's a classical algorithm called OLIVE, which uses successive elimination mechanism, which achieves sample efficiency, but is not computationally efficient. And our algorithm is the first one which achieves both statistical sample and computational efficiency. And in terms of algorithm design, we propose to do a modification of the LSVI algorithm. And in specific, so similar to classical LSVI, we first solve regression task using the current data, and our goal is to estimate the right-hand side of the Bellman's equation. And so suppose this blue line is the right-hand side of the Bellman equation, the regression target, and the black line is a point estimator constructed by LSVI. We additionally propose to quantify its uncertainty by constructing a high probability confidence region surrounding the black line. And the width of the uncertainty region is given by this gamma function, which can be computed in closed form for both kernel and neural network. Then we propose to add this uncertainty quantifier to the black line and get an upper confidence bound given by this red line. And then we will update our policy using the greedy policy with respect to the upper confidence bound. And by doing this, we directly make a trade-off between exploration and exploitation. Intuitively, we take any action either because the LSVI shows us that the value is large, which means we are exploiting, or it's because the uncertainty is large, so we are doing exploration. And also we can show that this algorithm, this Q function is always an element-wise upper bound of the optimal value function, which gives us the name of optimism. And I will skip, in the interest of time, I will skip the construction of the uncertainty quantifier, so which intuitively is given by the Hessian of the ridge loss. And in terms, and finally, I would like to present our theory where we show that this algorithm achieves square root of t regret and depends on the horizon quadratically. And also there's a term that quantifies the complexity of the function class, which depends on the effective dimension of the kernel and the log covering number of kernel, which these two can both be computed using the eigenvalue decay condition of the kernel. And when it comes to neural network, the kernel boils down to neural tangent kernel of the neural network. And and for neural network, we have an additional term which goes to additional approximation error term, which decays to 0 when the width of the neural network goes to infinity. And our algorithm is the first one with a square root of t regret with neural network function approximation. And we only require the structural assumption that the function class has no approximation bias, which includes the right-hand side of the Bellman's equation. And there's no assumption about the sampling paradigm. And so that concludes my talk. Thank you very much.
Thank you, Joran. Due to time limit, maybe we move on to the second talk and leave the question to the end. Joran, can you please share your screen?
Sure. Maybe Joran can first stop sharing.
Yeah.
Okay, that works. 1 sec. Does it work?
Yep.
Cool. Okay, let me do the full screen. Well, thanks so much for organizing such a wonderful seminar, and thanks, Professor Song, for inviting me. So this talk is based on joint work with Yingjing at Stanford and Joran Yang at Princeton, who will move to Yale. So I'll talk about the opposite philosophy, compared with Joran's talk. So I'll talk about pessimism. But the setting is different. So we focus on the offline reinforcement learning setting, where we're given a data set and we'll try to learn a good policy out of it without any exploration further with the environment. So I'll first briefly go over the same thing, which is the episodic MDP setting. And in particular, I'll focus on the offline setting and introduce the difference with the online setting. And for the offline setting, there are specific difficulties, and which in particular arises from the epistemic uncertainty. So the setting is the same. So we have a we have an agent which interacts with the environment. So the agent can take the action, and the environment will return a state. And then the agent receives the reward, and then the environment transits into the next state. So there are several key components here. One is the infinite state space, which makes the problem very hard. And for simplicity, we'll assume finite space, action space, but the action space can also be infinite, up to some modification to the algorithm. And we assume unknown reward function and unknown transition kernel. So assuming if they are known, then we can just solve the MDP and obtain the optimum policy. So the difficulty actually arises from estimating those unknown quantities. For simplicity, we assume a finite horizon setting, and MDP terminates when we have H steps, and then supposedly we will start another episode. But for the offline setting, we can only have K episodes in total, and we cannot interact with the environment more. So here is a more detailed interaction with the environment. So we execute the policy which maps from a state to a distribution over the action space. And then by taking this policy, we are transiting into the next state, and then we take another action and receive the reward. And we go on until the capital H step. And then we collect the total reward and call it J. And we want to maximize this J over the pi. So that's the policy that maximizes the expected total reward. That's what we want. So by the dynamic programming principle and the Bellman equation, we can just solve for the Q star function, which means the optimal value function. So we have a very nice recursion known as the Bellman equation, which says that at each step, you can just take the greedy policy, assuming we have the Q star, then we would have the optimal policy. And then we can do this recursively, and then we would have the optimal Q function for the previous step. So we summarize the entire Bellman operator as B, and then Bellman equation can be written in a very compact form, where we're doing this recursion of Q star. So at each time, we optimize the action over the Q star H plus 1, which is the optimum Q function of the next step. And doing this recursively, we would obtain all those Q star functions for each step. And also we can obtain the corresponding optimum policy by taking the greedy policies. And we'll focus on the function approximation setting where we're using a rich function class like linear functions, neural networks, and reproducing kernel Hilbert space to approximate this Q star function. Right, so this is essentially the same setting. The difference here is that we focus on offline learning, which means that once the agent has already collected the data set, or sometimes the data set is given to the agent, then afterwards, it cannot take any action against the environment, and the environment will not return the next state or any reward. So we only have the data set and that's all. So it's collected beforehand, and there's no more data. This data set collected could be very arbitrary in the sense that, for example, there could be an experimenter that does a lot of, for example, trials, and we do not know the rules for those trials. So we cannot ensure the quality of this data set. And because we cannot interact more, we cannot correct for the bias, for example, in this data set. And our learning objective is still the same. We want to obtain an optimum policy that maximizes this expected total reward. And at the same time, we want to minimize, we want to obtain this pi hat, which is an estimator for this pi star. We want to minimize this suboptimality gap. So the algorithm just takes two input. One is the data set and one is the function class. And X here is the initial state. For example, we can think of a fixed initial state for now. So the Bellman equation actually motivates us to do a very simple algorithm called value iteration. We can just do the recursion. So because of the function approximation, at each step, we're just using this Bellman operator applied to the next Q function. But here we only have Q hat because we are having an estimator instead of the Q star itself due to the unknown reward function and unknown transition. So we can only estimate, the population quantities using the data set D. And we have the function class, which, we're just doing regression over this function class. Okay, so that's the estimation step. And once we have the estimator, then we can do the optimization step. We just take the greedy policy. And this is a naive algorithm, which serves as a template for both online setting and offline setting. But we will see that this breaks in the offline setting, well, and also online setting as well, as Jordan has mentioned. So essentially for this very naive algorithm where we're doing this estimation and optimization alternatively, and then we're doing the recursion across different age, we hope for several things. The first thing is that we hope we can get a good estimator, right? In the sense that assuming the data set is very good, assuming a lot of density lower bound conditions, then we can get a good estimator for the Q star function. And also, we hope that this optimization step can perform well in the sense that we can obtain the max. This should be easy when we have finite actions. So we kind of abstract away the difficulty of this step. So it will become difficult when we have a continuous action though. And then combining those two, we hope to get a good actual performance, meaning that our expected total reward for this estimated policy will be very close to the expected total reward of the optimum policy pi star. Okay, so that's the underlying philosophy for designing this algorithm. But in reality, this type of algorithm often fails, even in the single stage setting where we have a multi-arm bandit example. So think about the Gaussian bandit, where for each arm, the reward follows a Gaussian distribution with a certain mean, which is the reward applied to this action. So this is the reward function and takes a certain value for this action. Okay, and then we have a variance of 1. And in total, for example, we can have a lot of arms. Let's say in the pre-collected data set, we just observed pooled actions and the collected reward. And each action can be put NA times. So this N here is just a counter, right? And then we can follow the naive value iteration algorithm. Now we do not have to do the recursion at all. We just can take the average, to estimate the mean, and then we can take the greedy policy. But you see, this algorithm can fail miserably because sometimes, we can just have a very bad arm, and it turns out that this bad arm can be just put like 1 time or 2 times. right? So in reality, this happens a lot because, for example, if you're trying a lot of drugs, then there could be a bad drug then that is only tested once or twice. Then there is a probability that because we only have a very small n, the sample average will have a very large deviation from the real mean, and by chance, this sample average will turn out to be very large. So it means that it will look very good just by chance. So as in the following example, so for example, I have an arm, right? It is just the mean is just a 0, and it is just observed for a few times, and then the sample average could have a very large variance, and as a result, it can just be by chance that this mu hat, which is the sample average, is very, very large, and just then if I'm just optimizing over different actions, then probably I will think this action will be the best, but it is indeed not, because my best action is the first arm. Okay, so this kind of situation will be very common if I have a lot of arms, and also for several arms, my observation, my sample size is very low. Okay, so this is the essentially the fundamental challenge. So we call it the epistemic uncertainty because it means that we lack observations on several of the of the instances or of the arms. So in general, this phenomenon can be summarized as follows. So the policy is just insufficiently covered by the data set. So for example, we have large uncertainty in our knowledge about a certain policy, and this policy can sometimes be a very suboptimal policy. And as a result, we observe a notion of so-called spurious correlation. So it means that this pi hat, which we use as our obtained policy, could correlate with those suboptimal arms and with the data. So roughly speaking, we can just think of the definition. So we have the J, which is the expected total reward, and we have the pi hat. We hope that this quantity is very large, right? Because if you plug in the estimated policy, then we hope the expected total reward is high. But the problem is that this policy is obtained by optimizing some J hat. But J hat is very inaccurate. It depends on the data set. And then my obtained policy would correlate with the error within this J hat. And we call this spurious correlation. And in the previous example, this J hat could arise from the arms that are observed less often. Then it will be very bad if we find a pi which actually have a lot of uncertainty, and it just turns out to be very good just by chance. Okay, it is indeed not very good, but we just our observation is that it is very good. Okay. Because we do not have further interaction with the MDP, and as a result, we cannot reduce this type of uncertainty. And then the idea is that we have to be robust against this type of uncertainty to obtain a relatively good policy. So in the classical literature, the usual assumption that get rid of this type of spurious correlation is the assumption that we have a uniform coverage for all policies. It means that our data set is sufficiently good in the sense that it can cover all states and all actions for sufficient many times. And then for any policy, we can evaluate this J or the Q function sufficiently well. But this type of assumption might be just too strong and unrealistic. So then the question we try to answer is to design a provably efficient algorithm for offline RL without posing too much assumptions on the data set. So the solution is by pessimism, where we are trying to penalize a large epistemic uncertainty. So for example, if we think about the Band-Aid problem where H equals 1, we only have one stage, then it means that we want to penalize those arms that are visited less in the offline data set. There could be several situations. For example, we certainly do not want the situation where we have a very high estimated value and also high uncertainty. So that creates the spurious correlation. And also we do, sometimes if we have a high estimated value, but low uncertainty, that's the setting that we desire, but it totally depends on the data set, whether or not we're able to see this kind of data point. And then, you know, a more common situation is that we can get a relatively good estimator, you know, and also with a low uncertainty, and also the estimated value is sufficiently large. So then we'll just take this R or take this policy, and then we can use this as an approximation for the optimal policy. So a solution is called the pessimistic value iteration algorithm, where we are trying to incorporate uncertainty quantification into the value iteration algorithm. So, you know, it is very different from exploration in the sense that now we're subtracting the uncertainty just to be robust. And then we'll briefly, you know, introduce why pessimism helps from a theoretical perspective. And then if we have time, we will try to see the special case of this pessimistic value iteration algorithm for a class of MDPs called linear MDP. So pessimism is known to work in practice in a lot of different settings. For example, there are model-based algorithms and value-based algorithms, which achieve the state-of-the-art performance in the offline RL benchmarks. And in theory, there are also several related works, for example, regularized fitted Q iteration, where we are trying to restrict the policy class to be close to the behavior policy, which is kind of different from our approach. So also there is another paper which analyzes the importance of pessimism. So there the algorithm is similar. So in this work, we introduce a principled framework for incorporating pessimism, and we do not restrict the policy class, which is unlike the first related theoretical work. And also we do not restrict the coverage of the data set. So we just use the, you know, some kind of uncertainty quantifier to adapt to the coverage of the data set. And compared with the second existing theoretical work, we actually show the optimality of pessimism in the sense of information theory, although we're not able to cover that in this talk. So the algorithm here is, you know, we're just trying to incorporate uncertainty quantification in the naive value iteration algorithm. So the first step is still doing regression, where we're applying this Bellman operator on the next Q function as the regression target, and we're trying to do the regression on the data set and over the function class F. And once we have obtained this estimator, we can quantify its uncertainty. So we can construct a uniform confidence band, which has the width of gamma. So gamma depends on the input. So gamma is also a function. So here the equation is for each state and action, and also for each H. So H is which step within my entire horizon of capital H steps. Then we're using this lower confidence bound. We're studying this estimated Q function, not as my prediction, but instead the prediction minus the confidence bound. And this penalizes the uncertainty. So if I have a large epistemic uncertainty on a certain state and action, then I'll have a very large gamma. And then because I'm trying to be robust against this kind of uncertainty, I certainly do not want you know, some kind of overshooting situation. Then I'm subtracting this penalty, and then I'm using this Q hat function to guide my decision. For example, if I'm trying to take the greedy policy, then I'm certainly using this Q hat, which has already subtracted the uncertainty instead of this Q bar, which is just the naive estimator, which could introduce the spurious correlation. And then the question is why it indeed helps, right? So for example, we can certainly think about, right, taking the upper confidence bound, which in the online setting actually helps with the exploration. But in the offline setting, we're trying to take the lower confidence bound. So here's a more concrete theoretical analysis. So everything actually arises from the so-called model evaluation error. So it takes the difference between our regression target, right, applying this Bellman operator on the next Q hat function, and our estimated function, which is the kind of output of the regression procedure. So that's our prediction. Okay, and although we expect them to be close, but on certain state and action, due to the lack of observation of those state and action, there could be a gap, and that gives us the error. And by the construction of this kind of pessimistic value function, we hope that this error can be upper bounded by 2 times the width of the confidence interval. Okay. And then we hope to use this gamma, which is the width of the confidence interval, to dominate this model evaluation error. So more concretely, here it's getting more mathematical. We can decompose the entire suboptimality, which measures the gap between the expected total reward of the optimum policy and the policy we have obtained, which is called pi hat, right? And evaluated at a fixed initial state. So we do not have to worry about which x it is, it's just given initial state. And then the decomposition takes the following form. So it says that the entire suboptimality can be indeed decomposed into 3 terms. The first one is the spurious correlation, which is the quantity we have seen even in the 1-stage setting, which is a special case of MDP. Okay. So here we're taking the expectation with respect to the obtained policy, and it correlates with the model evaluation error, because I'm trying to obtain the greedy policy based on data, and here the model evaluation error also depends on data. So another term is the so-called intrinsic uncertainty, which is the thing we cannot avoid. So those are the uncertainty along the trajectory of the optimum policy. So it means that if we do not observe a lot of data points along the optimum policy, then there must be uncertainty for estimating the optimum policy, which we cannot avoid. And the third term is the optimization error. So if we are using a greedy policy, then it is easy to see that if pi hat is greedy with respect to q hat, then this term will be negative, or at least non-positive. So then it means that we only have to worry about the first 2 terms, and we hope to eliminate the first term. So if we are actually using a pessimistic value function, then the model evaluation error will be bounded between 0 and 2 times the width of the confidence interval. As a result, the first term is always non-positive. And also, like I mentioned, the third term, if we are using a greedy policy, which means we're doing the optimization sufficiently well, then it is also going to be non-positive. And then we have a very clean suboptimality bound, where we are only dealing with the second term, which is the intrinsic uncertainty. That is the thing that we're not able to eliminate anyways. So in our paper, we have a more formal statement of what we mean by we're not able to eliminate this. So it's an information theoretical argument saying that this is essentially the lower bound. So if we're using pessimism, then this term becomes 2 times the accumulation of this width along the trajectory of the optimum policy. And this is essentially an optimal bound. So in other words, we can obtain a quantity that only depends on the optimum policy and the associated uncertainty. And in particular, the pessimism procedure actually eliminates the first term, which is the spurious correlation. That's why we're able to avoid the bad case in the Gaussian bandit example. And then we'll go into more details about how to construct this uncertainty quantifier for the linear and DP example. So we'll only briefly go through the setting and detail here due to the time limit. So linear NDP is a very specific class of NDPs where the transition kernel admits a linear decomposition. So it can be factorized into a feature mapping of the current state and action, and also another feature mapping applied to the next state. So the good thing about linear NDP is that if you apply the Bellman operator on the next Q function at the h+1 step, then we have a linear function. So phi is this phi feature mapping here, and theta is the parameter we're trying to estimate. So also sometimes we'll assume a linear structure on the expected reward as well. But if the reward is known, then this is not necessary. So the major difficulty comes from the structure of the transition kernel. And Due to the structure, we'll be using a linear function class to approximate the value functions, Q or V. V is the value function on a certain state. And then this procedure boils down to first do the estimation via ridge regression, and then we can use some closed form to quantify the uncertainty. Right? So this is the form of the confidence interval for linear regression. And then here, this lambda matrix is just the sample covariance matrix up to some normalization. And then we can subtract this uncertainty quantifier obtained here from the estimated value function, and then take the greedy policy, and then do this recursively for capital H steps. And then we will obtain the policy for each step. And then as a special case, as our previous theorem, so we can just directly plug in the form of the confidence interval here, and we obtain a very simple upper bound, and we're just accumulating the width of those confidence intervals, along the trajectory of the optimum policy. And the only assumption we require is that the data set is compliant with the underlying MDP, which essentially says that the data set is generated by the underlying MDP, no matter what the behavior policy is. And we do not assume a sufficiently nice behavior policy. So this is a kind of oracle property like we have handled in statistics. So it automatically adapts to the trajectory of the optimum policy. And the guarantee only depends on how well this pi star is covered in the data set. And we do not require the coverage of any trajectory, for example, the trajectory of a suboptimal policy. So far, the upper bound is data dependent, although in our paper, we have several special cases, specialized, which essentially like characterizes this upper bound when we have a certain property of the lambda matrix. But this, on the other hand, characterizes our best effort, as we have a information theoretic lower bound saying that this is the best you can do. So here are the special cases. I think I still have 2 minutes. So we have the several special cases. For example, if assuming, for example, we have a well-explored data set, meaning the data set can uniformly cover all policies, although this is very challenging to achieve in practice, then we can obtain a 1/√K, which is the usual rate of convergence in statistics, if we have IID observations from a certain behavior policy, and we have some kind of minimum eigenvalue condition. But like we mentioned, it's really hard to collect such a data set. So the nice thing about our upper bound is that if we have a so-called essentially explored case, where we only have a good coverage of the optimum policy instead of all policies, then the suboptimality can still be upper bounded by 1/√K up to some coverage condition. So here we do not assume some kind of uniformly lower bounded eigenvalue, but just assuming this lambda matrix is lower bounded by another matrix, which is the covariance matrix along the optimal trajectory. That's a much weaker condition. What I'm not able to cover here is that this upper bound is also information theoretically optimal, in the sense that we cannot do better. So in other words, this upper bound contains all those essential information about the optimum policy in D. In a sense, we adapt to the essential information and get rid of the spurious correlation. I guess I'll just stop here, and if there is any questions.
Are there any questions? We may have time for one quick question. Okay, if not, we can move on to the third speaker. Hosam, are you online now?
Yes, I'm here. Right.
Great. Hosam, thank you so much for being here in your early morning. I have introduced you before you joined, so please get started.
Absolutely, thank you. Let me share my screen then. Just give me a minute.
Yep, we can see it.
Perfect. Okay. So good morning, everyone. Thank you, Ray, for inviting me. Today, I'll be presenting 3 papers from our research. So again, I am Hussam. I'm a principal scientist at Amazon. And the cool thing about these 3 papers is that all 3 of them were basically pioneered and led by interns. So we will start with the first one, solving inverse reinforcement learning. It got published in ICML last year, and it was led by Sinong. So solving inverse reinforcement learning is a big claim. Let me remind you of what inverse RL is. So the aim is to recover a hidden reward function from observed agent demonstrations. A common example is autonomous driving. You record the driver, right? The driver drives around, right? You apply ARL to uncover the driver's decision process and then apply it on novel scenes. And so basically, ARL, instead of trying to code what is the utility function of stopping at a light signal, of crossing lanes, turning right or left, you don't do any of that. You just record it, and ARL attempts to uncover all of this automatically. Now, recovering this reward is not as easy as it seems. Given a reward function, usually an agent follows a policy and generates demonstration. So in the car example, you as a human, you are basically sitting in this car and you're driving around. So you are generating observed demonstrations for ARL to learn from. And we assume that you are basically a good driver. So you are following an optimal policy. Now, what happened is that ARL attempts to reverse engineer the rewards based on these demonstrations. A major issue is that different reward functions could explain the observed demonstrations equally well, making it impossible to identify the true underlying reward function. You end up basically identifying a set of reward functions, right, that are equally plausible. This is called the identification issue. And this is a pretty, limiting issue and important issue in our case. So how do we solve it? We basically add the concept of an anchor action. For each state, an anchor action is an action whose reward is known a priori. This is a key assumption in our method. You may object, hey, it's very restrictive. No, it's not. It turns out to be naturally satisfied in many situations. You can simply add the action of doing nothing with 0 reward, and that's it. You have an anchor action. Now, how are we leveraging that? Well, you have your agent who is now following an optimal policy, getting observed demonstrations. With our method, and with this key assumption, our method, which we call PQR, which I'm going to explain in a second, basically allows you to precisely recover your reward. And so we solved the identification issue. Now, notice in here that we are allowing the reward to depend on both state and action, not only on state, as other restrictive inverse reinforcement learning methods assume. Now, ARL assumes that demonstrations result from an optimal policy, but it's impractical, right? Usually when you're driving your car, you sometimes make errors, right? Accidents happen. So it's impractical to assume that agents always make the best choice. Unfortunately, this is a limitation of ARL. How can we solve that? Well, we remedy that by assuming that agents maximize and follow something called energy-based modeling. Under this paradigm, the optimal policy itself is stochastic. And you can see the formula in here. It's a softmax. And basically, under energy-based modeling, it allows for randomness in the agent behavior under the optimal condition and is more realistic. And so now you are not doing the exact best action. You are following the best action with a high probability, right? But we allow room for error. Now, if you really care about the exact best policy and you want something deterministic, like in classical ARL, well, this can be solved for you. You simply have to have alpha go to 0 or epsilon close to 0, and then you have your standard ARL with optimal policy where the agent never makes any error. Any questions so far? Okay. And please feel free to stop me at any point. I'm happy to take questions at any point. So we call our method PQR because we sequentially estimate A, the policy, B, the Q function, 3, the reward, PQR. The first step is to estimate the policy. And for that, we use any stochastic policy estimator for energy distribution. There's a couple that are off the shelf, any prior one, pick one, apply it, right? So there's no novelty in choosing the policy. The second step is where the policy is, where the novelty exists. It's basically where we do the Q estimation. Here we ran into the identification issue. A wrong Q will induce a wrong R. This is called shaping. And we really care about getting the right R. Right? And so what we do is that this is where we leverage the anchor action assumption. Because we have this anchor action, we are able to solve a fixed point contraction to uniquely estimate the Q for the anchor actions. So now I know exactly what is my Q for every anchor action, state anchor action tuple. Now transitions are usually unknown in practice, right? And so what we do is we use a deep Q network strategy on which we apply the contraction repeatedly over demonstrations. Basically, so this is where the deep PQR comes in. Basically, we say, okay, we don't know the transition, so we learn that from the data, and we use a deep RL strategy, right, to be able to have a flexible structural learning on that, right? So we're able basically to estimate the transitions. So this particular method is called fitted Q iteration, and the previous speaker did mention that in his talk, right? And so we use a fitted Q iteration if the environment transitions is unknown. Now what we end up is we have a policy and we have a Q function for every state action tuple. These turn out to be sufficient to uniquely identify a Q function for every state action tuple. Not just for the anchor action, right? Any state action tuple, we're basically now able to identify a proper Q function for it without shaping. The final step is we're using a policy and Q function estimate. We can recover the reward using supervised learning, right? So basically here, this is again, no novelty in here. You just have your policy, you have your Q functions, and just use any standard supervised learning algorithm that you like to recover your reward estimate. We use deep neural networks, but you can use whatever you want. Yeah, and so this is basically how the algorithm work. And this last function, you basically iterate over the data itself. So you have, the estimation is over the observed data. The expectancies over the observed data. So how do we do it? In the paper, I'm really glossing very quickly in here, but we provide theoretical guarantees. It basically said that there's a non-asymptotic upper bound on the estimation error for PQR, which is usually a desirable property. B, in practice, so the results show that it performs very well as compared to other inverse reinforcement learning methods. And so in the graphs in here, lower is better because this is the mean square error. And every one of these is basically, as you go to the left-hand side, the problem becomes more and more complex. So the state feature dimension increases. And we can see that PQR basically starts with near 0 MSE. It increases a little bit, but it's always pretty small. It's always below 1, while other methods pretty much increase almost exponentially. Questions before I move to the next paper? Okay, I will move on. And if there are any questions in hindsight, please feel free to jump at any point. In addition, any follow-up, please feel free to email me. I'm always open for for follow-ups and thoughts, comments, as well as collaborations. So the second paper is Bootstrapping Bandits. It is a paper that was led by Sari. Again, it's one of my previous interns and collaborators, and it's forthcoming at Management Science. Suppose you have an ad with multiple slots. And I'm taking here basically an ad about your biking team, and you are unfortunate enough to ask me to design an ad for you for your biking team. I'm a very lousy ad designer. And so basically what I say is, okay, I want to give you an ad, but I want to have it modular. So I have multiple slots. Each slot, I will have multiple variants in it, multiple alternative variants. And so at the end of the day, basically, when I give you an ad, it's a combinatorial explorer. Right, so I give you basically, here's the layout, and here's the number of slots, and here are a bunch of variations. So you can pick among basically 100 different layouts. Hopefully, one of them will be to your liking. The way that we present these features basically are a representation where we capture all pairwise interactions as second-order features. So basically, I'm saying, okay, I have a particular image and a particular title. Any image-title combination is a feature. So this is how I am featureizing this ad. In this simple example, we have two categories of features. First order features. So these would be something like the image, the title, the button, right? And then the second order features. So these are the combination or interaction between first order features. Image 1 and title 2, image 1 and button 1, and so on and so forth. We concatenate them to form our final vector. So this is how I am featureizing this particular ad generation problem. We feed all of this into a Bayesian generalized linear model, where each feature is associated with a distribution. Right? These distributions and these weights are generally start with a non-informative prior, right? Because this is a Bayesian model. So every weight has an underlying distribution. This distribution will shrink over time, but has to start somewhere. Where do I start? I start from a non-informative prior. Basically, I take a standard Gaussian N0. This is pretty ubiquitous in the literature, right? And you can see basically how this soon will become a bandit. Now our question is, can we leverage the data to start from an informative prior instead? Why am I starting from N01? Can I start from something more informative, leveraging my own data? So notice that our features can be divided into two categories, category 1 and category 2. In our use case, it's first order features, second order features, but the method applies to absolutely any feature grouping of your liking. Could be like item features versus content features, whatever, right? Global versus local features, whatever feature grouping you may have. And then I basically impose a hierarchical meta prior over them. I'm basically saying, listen, every category, instead of getting its own an informative prior, I'm saying it's basically coming from a common hierarchical meta prior, one meta prior per category. And now basically my problem becomes, how can I compute empirically the meta priors from the data itself, right? And so how can I seed my system? And so here is how our empirical Bayes algorithm works. We basically start from the standard generalized linear model, knowing nothing. We just have N01, no informative prior. We aren't adding anything. We run it for a day, right? We basically start showing these ads to people. People click on them. We collect it. So nothing fancy. We even, train this model a day or two or whatnot. And then basically, as I'm training this model, I am computing empirically. I have enough data now to compute empirically from the data itself these hierarchical meta priors. I'm not acting on them yet. I'm just computing them and putting them somewhere else that is not related to the model. Once basically I have a good enough estimate of these hierarchical empirical meta priors, I save them and then I restart my model. But this time I restart my model with these empirical priors that I computed from the data that this model has seen for the past couple of days. Because this data basically is a data that I saved, I can now rerun my model on this data that the model has already observed, right? Now this is past data. So all of this happens offline in minutes, right? And so basically, I take a step back in time, rerun my model using that data after seeding my model with the proper empirical priors. And now basically I have a better moment. I come back into the current moment, right? And so now I have a better model that has used the data twice. First time to seed itself with empirical priors, second time to train on this data. And then basically I continue running as usual. How is this useful, right? Basically, the whole idea here is that you are trying to start your search. This is what the priors are, right? So basically, where do you position yourself in the search space before you encounter any data? And so because I was able to bootstrap myself, use this data twice, I placed myself in a better starting position in hindsight, right? Based on the data that I observed. And so what this graph is showing us is a longer reset time helps. Basically, if I restart my model after 1 day of data versus after 3 days of data, a 3 day of data help better position me in the search space. And so here lower is better because that's log loss. And you can see that the blip based 3 day is the lowest one. So this is the one where I restarted my model after observing 3 days of empirical data. Number 2, so this is an actual live experiment. And so this is the bandit. So basically here now I have my standard bandit that is operating over a generalized linear model as usual, versus a bandit that is based on this idea of self-bootstrapping using empirical data to better start my search space. And so the standard bandit is in blue, the empirical based bandit is in red. Here, higher is better because it's I'm measuring the cumulative success rate. And we can basically see that the empirical based bandit converges faster, right? In 5 days as opposed to 8 days, and is more stable. So these are some of the benefits basically of figuring out where to start. Now, this method only works if the data is not large enough. If you have a large number of data, right, you'll probably converge on day 1 or day 2, right? And so the benefits of this method don't go. If you read the paper, we have much more analysis, and we have a graph basically that shows that in low data regimens, the benefit of a better start can extend up to a month. Questions? Okay, and move forward then. So the third paper is adaptive recommendation. It was led by Ari and was published in KDD 2 years ago. So suppose I want to search for an item, but I have no idea how to describe it. Shaki-chan is perplexed. We have no idea how to describe this white star, right? But if I give you 2 choices, you can tell me which one is closer to your target item. And so in this particular example, the white circle is closer to the white star because they are both white, right? The black circle is further away from the white star. Now, in your feature space, you can actually represent that based on distance metrics. You can basically say, what I just described means that the distance between the white star and the white circle is closer than the distance between the white star and the black circle, right? We can even mathematically represent the probability of a user picking item A over item B given the target. And so here, given the target, which is the white star, I have a higher probability of picking the white circle over the black circle. If I observe a bunch of preference pairs, I can compute the likelihood of an item being the target, right? And so basically, if I just, and remember, I do not know what the target is because you can't even know how to describe it, right? It's very hard to describe. And so I just show you a pair of items. You tell me which one is closer to your target. Based on these observations, I am able to compute the likelihood of a given item to be the target, right? If I can do that, I can then sample out of it. And again, a common method in all of these methods is that eventually, because we are sampling, we will eventually make a bandit out of it, right? No. And so here's a toy adaptive real-time search application. Say our feature space has 2 dimensions, pointiness and color gradient, and we need to interactively find the target in the user's mind. So let me populate the space for you. Here's our items, and the target item is at the top right with a red arrow, right? So it's the same item that Jackie Chan was searching for. It is basically our white star. The system has to present 2 items for you at random, right? The user picks the one that is closest to the target item. And so in this particular example, right, the user is going to pick the lighter shade of star. And so what we do is basically we shift likelihoods, right? So the system recomputes the likelihoods. And now there's part of the system, part of the search space that has lower likelihood. So here I shadowed it. Note the shadowed items are not eliminated. They basically only have reduced likelihood mass, right? The system can still pick from them. And as the experiment goes, eventually we may be even able to pivot, right? And so we repeat, the system picks 2 other items. You basically say, okay, the star is even the closest, right? And so we shadow a bigger part of the space and so on and so forth. So we shadow more. And then finally, the system shows you your target, and then you pick it, and the experiment is over. Okay? And so, in reality, we show a slate of recommendations, and not just 2, not just like 2 items to pick from. And we apply the algorithm in an embedding space, right? So the actual problem at hand is much, much more complex than the toy problem that I showed. But our representations allows for a fast point-wide target estimation because I'm working in metric space, right? I'm able to quickly have point-wise estimates for every single item in our space or in my catalog. But how do I choose the items to present to the user in real time? We have a very large catalog, and proper contextual bandits are slow. If basically I want to have a bandit with every item of the catalog being an arm, it will take me some time to train every single time you pick or you click. So I cannot basically present this to you in real time. And so here's our solution. First, we generate discrete distributions using softmax equation, or eventually we will, right? So the way that we do it is that let's focus on the formula for a minute. G is the likelihood of the star. So this is my point-wise estimate, and that's fast. This is what I explained in the first part of these slides, right? B, this is basically the number of interactions with an item. So this is basically my cheap way of estimating a variance and adding some uncertainty in the system. Modeling the uncertainty in the system, right? So basically, if you think of annealing, this is the temperature. C, I add a Gamble distribution. So basically, I'm getting to the Gamble softmax trick. By adding a Gamble distribution, adding it to my pointwise estimate, effectively, this is mathematically equivalent to having a softmax. So if you do the argmax of a Gamble, this is equivalent to having a softmax, right? So basically, I'm recovering my softmax distribution. And you may remember from 2 papers ago, right? The first paper that I was describing. If I have a softmax, basically I can sample out of it. I can even have a bandit or reinforcement learning method out of it, right? And so what I did in this particular equation here is that basically I'm able to generate discrete distributions using a softmax equation through the Gamble softmax tricks. And I'm adding the bandit uncertainty estimate through annealing. All of this boils down to I am emulating a contextual Thompson sampling bandit behavior using a cheap, fast, non-Bayesian, non-contextual technique, right? So basically, this is your poor man's version of a proper contextual Thompson sampling bandit. Why am I doing all of these jumps? Why I'm getting to the poor estimate? Because basically of latency, right? This is very fast. Your proper contextual bandit is slower. How is this doing in practice, though? right? And so here, lower is better. Our approach is Boltzmann, right? So Boltzmann is a fancier name of softmax exploration. So instead of saying softmax bandits, it's a Boltzmann bandit. So these two are equivalent. And so here, lower is better. And I can see basically that our approach basically is the lowest over the 4 completing approaches. In this particular graph, higher is better, because here I am measuring recall. How well am I doing at actually showing the user the item that the user had in mind? And so higher is better, and we can also see that basically our approach dominates. And so this brings me to the end of my talk. I'm happy to take any further questions. Here's my webpage. You can check the papers on my webpage. Here's my email. You can feel free to reach out to me at any point. Thank you.
Thank you, Hosam. I think we have a few minutes, so let's just open up a discussion for questions to all 3 speakers. I think we have let's see. Someone has a question, but I don't really know how to.
Do you want me to stop sharing my slides? All right.
That's okay. Oh yeah, I think someone has raised your hand. I maybe you can just speak.
Oh yeah, thank you. Just a quick question. I missed some point. Where is the bandwidth you were talking about? Can you go to that specific slide?
And in which paper? The 3rd paper, 2nd paper?
I think this paper.
This paper, here you go.
Mm-hmm.
And so effectively, look at that, right?
Mm-hmm.
What does Thompson sampling do, right? It basically samples from every single arm and takes the max, right? So it's argmax over the arm. Look at this formula. It's an argmax over a distribution. So that gamble, you're sampling from the gamble, right? And so in Thompson sampling, you have a proper underlying distribution. You sample from it. You do that for every arm, you pick the max. I'm doing the same. The difference here between this and the proper banded distribution is that the banded distribution, when you update it, you have to basically shrink this distribution over time, right? So the update of the actual underlying distribution of the banded will shrink its covariance. Here, I always have Gumbel 0, 1. And so how do I basically emulate the shrinkage of the covariance? This is basically where the temperature comes into play. This is the number of interactions with an item, right? That's the 2nd item here, C over N. Does this make sense?
Yeah, yeah. Just last question. How is it different from the Black-Scholes formula? Did you try to use some Black-Scholes formula for the environmental hazard sort of thing?
How is it different from what formula?
Black-Scholes.
I do not know.
Oh, okay.
Yeah, sorry.
Thank you.
Yeah, absolutely. And then if you look in the paper, like we have a bunch of theorems, we also have an appendix just dedicated to how to compute C, right? So there's much more details in the paper.
Where is your paper published?
This one, KDD.
I see. We can find the paper in the somewhere.
Yeah.
In your webpage. Great.
Yeah, on my webpage, all are public. All 3 papers that I just mentioned are public and freely available.